All right, so we are doing a review, and our review is for Organic Chemistry 1. And we're going to focus on the learning objectives that I posted in your modules. That I focused on these learning objectives as target areas that I think that you need to demonstrate that you understand. Okay, so I want to see some kind of demonstration of understanding in your final exam on Monday. Now your final exam is open at 8 a.m. When you sign in on your sapling, you get 50 questions. Okay, it's a 200 point. So that means it's going to score it out of 100 points. But I'm going to multiply that by 2 to put in your Canvas. And then that will be your final exam. Okay, so let's look at your topics for Organic 1. One other thing I want to tell you, when you log on to Sapling, you get exactly 2 hours. It's going to keep the time. You have to submit all your answers within that 2 hours. And you will not get the answer feedback. So this isn't going to be like your typical exams where I give you the feedback. And if you'd taken the ACS, you wouldn't get that feedback either. I do think since I wrote it and there's only 50 questions and not 70 questions, I think everybody will do well. Okay, so one of your learning objectives, let's just kind of focus on naming. So you're going to get about 5 naming questions. And so to review some naming, I chose a few examples. So let's look at this. So if you have a structure like this, CH3, CH2, CH2, CHO, that's a Lewis structure or condensed structure, and you need to be able to convert it into a Lewis structure. That's what you'd want to do first. CHO is an aldehyde. And then once you do that, then you name it. Aldehydes get number 1 priority. 1, 2, 3, 4. So butane, we're going to drop the E and add Al. So this is butanal. You don't have to put the number for the aldehyde. So one of your learning objectives is functional groups. So you need to know your functional groups. That's an aldehyde. You have a slide. If you look in chapter 18, slide 11 of 83, it gives you the functional group priorities in naming. And so acids have the highest, so you find the longest chain including the acid, and then esters, and then aldehydes. Okay, so aldehydes, that's why you start with that as your 1. Then ketones, then alcohols, and then you have an amine. You have alkyne, it's a carbon-carbon triple bond, and an alkene, carbon-carbon double bond, and then you have alkanes. Below alkenes are ethers, and the lowest is the halides. So halides are just like substituents when you do naming. All right, so we're going to do a few more examples of naming. So that's kind of like your functional group and understanding the priority. You need to understand your prefixes and suffixes. So let's see if we can do another example. Okay, so what does this look like? We do our Lewis structure. We'll make it like this. How about this? Okay, so where are we? C, 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 CH, CH, CHO. Okay, so functional group here, we have an aldehyde, and that's highest priority. So 1, 2, 3, 4, 5, 6. So hexane, drop the E and add Al. That's our longest chain. Now we don't have any substituents here, but on carbon number 2, we have a trans. When you do your naming, that's E. So that would be 2E. And then if you come here, 3, 4, you have 4, and you see the hydrogens on both sides. So this is 4 cis, and cis is Z. Put those in parentheses. And then you would have to write, change the name here, 2, 4, hexa, diene, al. And this would be your name. Now keep in mind, you do have multiple choice, so that'll help you out too. Okay, another example. So that's cis and trans. So you need to be able to do cis and trans. We also have R and S. So let's look at some R and S examples. All right, so here we have a diol. As you can, so you start with the longest chain, 1, 2, 3, 4, 5. So 5 is pentane, and this is going to be pentane diol, okay? And we have 1 and a 2 dash pentadiene, diol. Now, you have one stereocenter. You see number 1 is not an asymmetric center. That's not an asymmetric carbon because that's a CH2. And one of your concepts in organic chemistry is assigning Rns configurations. So we're going to deal with that now. Assigning Rns, this is the concepts. And also determining the number of stereocenters in a molecule. So you only have 1 here. And so you have a hydrogen going back, you can put that in there, and you assign your priorities. Oxygen is 1. Now you have a carbon, and a hydrogen. So carbon would be 2. This would be the 2 because then it's carbon, oxygen. And then 3 would be carbon, carbon. And then 4 is your hydrogen because that's your lowest priority. And so you connect the 1, 2, 3. And you think about steering your car wheel to the right. Okay, so you're turning your car steering wheel to the right clockwise. And the hydrogen stays in back. So then that would be 2R. 1 through 2 pentadiene diol. Okay, let's do another example. Okay, so do we only have 2 stereocenters here? Yes, this carbon has 1 hydrogen, 1 hydrogen. This is not a stereocenter. This is not because the CH3s are the same. This is your ketone, and on your priorities, ketones have a higher priority. And so you find your longest chain. 1, 2, 3, 4, 5, 6, 7. 7 is heptane, right? Drop the E, add the on. Okay, so now we drop the E and we add the on for the ketone. So that would be, you could just do it like this. Different, you got the old school and older school. So hept and dash 3 on. That tells you where your ketone is. And then you have a substituent 4-chloro. And then you have a 6-hydroxy. And you also have a 2-methyl. Okay, so those are your substituents. And you're going to have to put those in alphabetical order. But before you put it all together, I would look at your stereocenters and assign R and S. So here, chlorine would be number 1. And then this is a carbon. This is a carbon. But this carbon's bonded another carbon. This is bonded oxygen. So that would be 2. And then 3. So then you connect what's coming at you is hydrogen. So 1, 2, 3. That's counterclockwise. So that would be S. But then you got to do a switcheroo because hydrogen's coming at you. So that's R. So 4R. And then we do the 6. This is a 1 with the OH. 2, 3. Assign your priorities. 1, 2, 3. Hydrogen's in back, so S stays S. So that would be 6S, parentheses. And then you put these in alphabetical order. Dash 4 dash chloro, dash 6 dash hydroxy, dash 2 dash methyl, heptan, dash 3 All right, so that should cover some of your naming with multiple substituents, prefixes, suffixes, applying R and S. Okay, the next one we have, the next concept on our list is analyzing spectra. Now you do have a lot of spectra to go over, and that we went over that in your lab, so you can go back and study that. That would be worth your while. The IR in your book is chapter 12, and then you have NMR after that, and I think that's chapter 13. So basically we're going to look at these compounds here. Okay, so we're going to look at these compounds, excuse me, and let's name them. Okay, so we'll name them. Then we also want to rank based on boiling points. And remember, the boiling points are your intermolecular forces. So you remember electrostatic are going to be your most, the hardest ones to take most energy to break. So these are going to be your highest boiling points and melting points. And then what's the next one? Hydrogen bonding. And then you have dipole-dipole. And then you have van der Waals. And if something has hydrogen bonding, it also has dipole-dipole and van der Waals. Okay, so as you move up here, you have them all. So in organic chemistry, your highest are going to be your amides for functional groups, and then your carboxylic acids. And then you're going to get into the alcohols and amines, because they do hydrogen bonding. And then your dipole-dipoles will be like your esters. So if you had to rank these based on boiling points, this would be number 1. And what is that compound called? That is a carboxylic acid, 2 carbons. So that would be ethan, drops the E, oic acid. And then number 2 would be your hydrogen bonder, right? And this would be propane-2-all. And then we don't have any stereocenters there. And then number 3 would be this compound. It's an ester. And that would be ethyl. So you name that part first. And then ethan, drops the E, and write 08 for naming esters. So ethyl, ethan, 08. Now, what I want you to do is, how would you determine them? How would you determine their difference in a IR? Well, this here, the carbonyl, would show up where? You'd see that it's around 1700 reciprocal centimeters. Okay, you would see you would also see this one at around 1700 reciprocal centimeters. So you couldn't distinguish between those two except what? This OH. The OH would show up as a broad around 3400 reciprocal centimeters. And you wouldn't see that in the ester. So you could determine the difference. So they'd have to have these two for the carboxylic acid. The ester would just have the carbonyl in its IR, and then the alcohol would only have the 3400 reciprocal centimeters. So that's how it's important to understand where your functional groups are, where they're going to show up, so you can distinguish between those molecules. And so that's one of your concepts, assigning molecules to spectra and understanding how to assign functional groups to IR. Now let's look at the NMRs of these compounds. So if we look at the NMR, how many NMR signals will there be? Okay, so for the first one, number of NMR signals. So how many peaks do you expect to see? Remember the equivalent? Well, you're looking at hydrogen NMR. There's one. So the first one you're going to get 2 peaks. Okay, you can draw them in there. I would. So those hydrogens are all equivalent. And then this hydrogen, there's 2 peaks. Okay, here, let's draw in our hydrogens. 1, 2, 3. 1, 2, 3. And you have 1 hydrogen here. So how many peaks would you get here? Well, these would all be the same, right? Because they're symmetrical. So that's 1 peak. That's another peak, and that's another peak. So 1, 2, you get 3 peaks in your NMR spectra for this compound. All right, you come over here, drawing your hydrogens, because we're assigning hydrogen NMR. It says 2, and this has 3. So these are equivalent. That's 1 peak, 2 peak, 3 peaks. This would have 3 peaks in NMR. How many proton? 1, 2, 3, 4. It should integrate out to 4 hydrogens. This one, 3, 6, 7, 8 hydrogens. This one, 3, 4, 5, 6, 7, 8 hydrogens. Okay. Now, what about the shifts, the ppm shifts? Well, if you're a hydrogen alpha to a carbonyl, you're going to show up around 2.2 ppm. If you're a carboxylic acid hydrogen, you're going to show up about 12 ppm. It's pretty far up the spectra. Over here, these are the hydrogen on the oxygen is going to show up about 4 ppm. This hydrogen on the carbons connected to the oxygen will show up around 3.2 ppm. And then these hydrogens that are connected to a carbon that's connected to a carbon are going to show up about 1.6 ppm. And then here, once again, we have the alpha carbon. These are going to show up, we said over here, 2.2, so that's about 2.2 ppm. This is hydrogens connected to a carbon that's connected to the oxygen. That's going to show up about 3.2 ppm. And then this is going to show up about 1.6 ppm. And then what's the splitting pattern? Okay, well, this one will be a singlet because there's no neighbors. This is the n+1 rule. This one would be a broad singlet. Okay, we come here. This hydrogen splits this one, so neighbor has 1. So this is a doublet. And this, of course, will be a doublet because they're going to be equivalent. And then this hydrogen here has how many neighbors? 3 plus 3 hydrogens. That's 6. 6 plus 1. So that would be like a heptet. Okay, it looked like something like this. Okay. What about this one here? This, there's no neighbors with hydrogens, so that's a singlet. Okay. This one here these two hydrogens, this neighbor has 3, so that's a quartet. Okay, that's a quartet. And then this one here, these 3 hydrogens, this neighbor has 2, so this would be a triplet. 1, 2, 3. So that tells you about equivalency and NMR signals, how many signal peaks you should get, the n+1 rule. Now let's do degrees of unsaturation. How many degrees of unsaturation for this first compound? 1. How many for the next one? 0. How many for this last one? 1. So what's degrees of unsaturation? How many does this one have? Okay, and let's talk about its NMR and IR spectra. And then so degrees of unsaturation are, you can read about in your book. You have a ring, so that's 1 degrees of unsaturation. You have a carbon oxygen, so you have a double bond, that's 1 degree. And then you have carbon-carbon double bonds, and you have 1, 2, 3. So you have 5 degrees of unsaturation in this molecule. Now, how many peaks? How many peaks would you see in the NMR? Well, you'd see this hydrogen. These would be equivalent. These would be equivalent. These would be itself. So 1, 2, 3, 4 peaks. Okay, what's the ppm you would see? Or this would be a triplet. This would be a triplet. This would be a doublet. This would be a singlet. This should show up about 9.8 ppm. The others would show up between 7 and 8 ppm because they are aromatic. All right, so that is all I'm going to do, all I'm going to say for analyzing your spectra. And now we're going to finish up the organic 1 concepts. You should be able to assign formal charges, resonance structures, functional group identification, ranking intermolecular forces, assigning hybridization. Okay, well, let's do that with that molecule just now. Okay, so hybridization. So this carbon here is bonded to 3 things. 1, not how many bonds, 2, 3. So sp2. You add the superscripts. That means this carbon here is sp2. Okay. Oxygen, put in your lone pairs. Has 1 thing, 2 thing, 3 thing. It's sp2. Put in your hydrogens here. Those carbons have 1, 2, 3. Those are sp2. Okay, so be able to do hybridization. Acid base, so let's do some reactions now. So let's do acid base reaction. And we will do this with, let's say, something like this. Okay, so sodium amide. So yes, you need to know your pK values, right? So you draw in your acidic proton. So this is your acid. This is your base. Can you draw the formal charge? The Lewis structure of this. Okay, so there it is. And this is going to come and take this hydrogen you're going to make your enolate, and that's also going to make your conjugate acid there. That's your conjugate acid. This is your conjugate base. And so we put the pKa of the acid here, and I believe that is, I want to say 9. You can look that up. The pKa of your conjugate acid is going to be 35. So your equilibrium arrow lies far to the product side. So acid-base reactions, that's how you do them. You assign your acid base and your pKa values. Okay, the other reaction we have on your sheet is free radical halogenation. So let's do this. Okay, so if you want to do your product here, you have right here a tertiary hydrogen, and this is going to have a lower bond dissociation energy. Do you remember the BDE table? So that's the one, and bromine is selective, so you're going to have a little bit of light here, and so the bromine cleaves homolytically. This is called your initiation step, and you get 2 bromine radicals. Now, the propagation step, you have to have your bromine radical. You should always have a radical plus a neutral molecule. And that is going to go and take that. Notice I have fish hook arrows here, okay, because we're dealing with 1 electron movement. And then you get a new radical. Okay, so new electron plus a H. Because 1 electron went with the hydrogen, the other electron comes from the bromine, and that makes HBr. Okay, and so that's propagation step 1. Propagation step 2, your newly formed radical then comes down here and just copy that radical, and then it's going to react with another Br, and it's going to do the fish hook, and that is how you put a bromine on a molecule, and then you generate a new bromine radical. That's propagation. That's the same thing as that right there. So that's your product. So your product is bromination at the tertiary carbon. So that's free radical halogenation. The other reactions you had in organic 1 are SN1, SN2, E1, E2. We'll do electrophilic addition of alkenes and alkynes, and that will wrap up our reactions. So let's look at these. So if you have something like this, okay, and you have 1 equivalent of sodium cyanide, what's your product? And what's the reaction mechanism? Well, this is a secondary and this is a primary. So the primary will react faster. So this is your nucleophile. You also have to know how to draw your reaction electron flow arrows. It's going to come after your electrophile, and the bromine is your leaving group. And this is your new molecule. That would be an SN2, backside attack. It's very important to understand that you get inversion of stereochemistry. So if you take like something like sodium cyanide, which is your nucleophile, and the nucleophile always attacks the electrophile. This is your electrophile. And you get inversion of stereochemistry. You only get this for an SN2. Okay, so now theta was coming at you. Now the N3 has to go away from you. That's the inversion. Okay, so that's an SN2 reaction. SN1. Okay, so let's look at an SN1. SN1 is usually something like okay, and usually it's something like Solvolysis. So let's put this in methanol. Okay, let's just actually do this. Okay, so this is your molecule. So what happens here is you have a good leading group. You have a secondary alkyl halide. So it could do SN1 or SN2, but you have a weak nucleophile. So you basically swamp it, you make that your solvent, and you get the carbocation, your SN1, okay? That is not your most stable, so you do your test, okay? That's a secondary. If it switched place here with that carbon, that would be a primary. Over here, if it switched places, so if we do it, it's called a this would be a methyl shift. There's no hydrogen there. This is a methyl shift. So now let's make this carbon red so you can see that it moved here and it switched places with the carbocation. Now methanol can come in as your nucleophile, and it will come in, and then you would basically get this molecule. Okay, so that's showing you the carbocation rearrangement that happens in an SN1. Also, another thing you need to pay attention to is when you're doing E2s. So let's do E2 and E1. A good E1 is just, if you take like a tertiary alcohol and acid. OH is a horrible leaving group, but it gets protonated. Okay, that makes it an excellent leaving group. It will just leave, and then you get a carbocation, which is the unimolecular intermediate, and now you're going to get the Zatsev's product. Zatsev's product means, so if you're going to, you take hydrogen from there, there, but you get the more substituted alkene. So that would be an E1. E2, let's take something like let's do this. Okay. And you want to react this with sodium cyanide. Oh, no, we're elimination. So we got to have base, right? All right, so what base would you want? Of course, a good one is sodium methoxide. Okay, that's a strong base. You get a negative charge. Okay, so this one, it's a chair. If it's an E2, then it has to be 180 degrees anti-periplanar for the elimination. So you're going to need to draw the chair. All right, so draw your chair. I'm just drawing my chair. All right, the bromine here is going down, and the isopropyl is going up. Okay, so the hydrogen that has to be taken has to be 180 degrees, so it has to be this hydrogen here. So then you have sodium methoxide comes and takes that hydrogen so it can push, and so then your product becomes and if you put this in two-dimensional, 1, 2, so that's your product. Okay, so and then you also want to review your Hofmann bases on page 364, and so you can look for a Hofmann, so like something like this, and if you had a base like diisopropylamine, which is a Hofmann base, that would actually take this beta hydrogen for an E2 and give you a Hofmann product, not a Zatsez product. So it gives you the least substituted amine, least substituted alkene. You also want to rank your alkene stability. That's on your concepts. Okay, the last thing I really wanted to go over was the electrophilic addition reactions, and also let's do a Newman real quick, a Newman projection. So what if you had to convert this Newman? Okay, so let's do this Newman. So that's our ketone that we talked about. What if you're looking down, your eyeball is looking down this bond? So that's 1, 2, 3, 4, 5. So you're looking down the carbon 4, 5 bond for a Newman. So let's make that your front carbon, number 4. We'll make that your front. We'll make the 5 the back. So that's going to be your circle. So do you remember the Newman? Where you have 3 things coming off there, and then your back carbon. This is circle here. This is in our most stable Newman projection, which is your anti-staggered. And then let's look at what's coming off of 4. You have Cl. So here you can put Cl coming here. What else is coming off of 4? This group here. So you can put that up there. C, O. Okay. That's coming off of 4. And then what you don't see coming at you is the hydrogen. So that's the hydrogen. And then you go to the back, you have an OH. Now OH is on the other side of your Cl. So I would put OH opposite of my chlorine. Also opposite of each other is this zigzag, the carbon. So this is your CH2, CH3. I put that opposite of my carbonyl, so a CH2, CH3. And then what you don't see is going back is the hydrogen. And that's how you do a Newman projection. Okay, and then your electrophilic reactions. Well, we also have naming. Okay, let's look at this real quick too. It's going to be a longer video than I thought. All right, so what's the relationship between these molecules? So you'll need to practice this. This is a Fischer projection, right? And I'm going to have 3. So we just need to look at chapter 5, kind of review some of these terms. Okay, so these are Fischer projections. Now this one has a plane of symmetry. So that's a meso. And let's assign R and S here. So this is 1, and then this would be 2, This would be 3. So 1, 2, 3. R, however, the OHs are coming at you, because remember this is bow tie. So that would be S. And then if you do the same thing here, 1, the chain is 2, 3, 1, 2, 3. And so, but keep in mind that's coming at you. So even though it's S, that's R. Now that's a meso. So what does that mean? It means they have stereocenters. So you still have stereocenters. That's why we did the R and S. But there's a plane of symmetry. So the molecule is achiral. So if you put it in a perimeter, it's not going to rotate plane polarized light. Now this one here, here's the 1, 2, 3. So that would be S, but this is coming at you, so that's R. And then if you name this one 1, 2, 3, S, but it's coming at you, so that's R. Okay. And then you come over here. This is 1, 2. So that's R, it's coming at you, so that's S. And then this one is 1, 2, 3. So even though that's S, it's coming at you, so that's R. Okay, so this one's RR. There's 2 stereocenters here, right? And this one's SR. So what are these to each other? These are, only one thing has changed. So they are enantiomers. Okay, so these are enantiomers. Okay, are these all isomers? Do they all have the same molecular formula but different connectivity? And their different connectivity is actually in space. That's why they're stereoisomers. And how is this one related? SR, RR, SR, these are diastereomers. Even though these are enantiomers of each other, this is a diastereomer to this, and this is a diastereomer to that. So you might want to practice some relationship compounds as well, because you'll get a question on that. And also ranking the stability of amines, not amines, the alkenes. Okay, so let's do some reactions. Okay, so I'm going to put some reactions up here, and then you can stop this and try to see if you can do it. So, and then you can check it. But let's look at something like this. Okay, and what would you use? What would this do? MCPDA. And what would that give you if you reacted that with sodium methoxide and then H3O plus? All right, so fill in that box. What if you react this with mercury acetate, and then you follow that with, and you put that in methanol, and then you follow that with sodium borohydride. Okay. What if you did mercury acetate in water, and then sodium borohydride? Hydrogen and palladium, and BH3THF, and then sodium hydroxide and hydrogen peroxide. And then do 2 more, Br, and then Br in water. I think, oh, one more, ozone, O3, and then follow that up with DMS. Okay, so let's see, how many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so if this makes an alkene to an alcohol, and it's going to give you the least substituted. So we'll put that here, and it's going to deliver a hydrogen here, and then the boron becomes the OH because hydrogen peroxide changes to OH. So it's very important that you have the methyl group and the OH anti to each other. MCPBA, that's going to give you the epoxide on one side. What if you react this with sodium methoxide? So epoxide opening, it's basic, so it's going to go the least hindered side. So that's going to give you OCH3, because it's going to come in from the top. And then that's going to force that to go like, nope. And it's going to get protonated here. It's going to give you epoxide opening. And that's under basic conditions. So the nucleophile comes in from the least hindered side. All right. Now we have the, this is the halohedron. So the first intermediate this makes is the bromonium ion. See how it's charged with the bromine? And then water is going to be your nucleophile. And this is going to come in from the more hindered because it's a delta positive. This is going to be at the Mark addition, Markovnikov. And so then you get the stereochemistry on that. It's going to come in opposite. It's going to come in opposite of your methyl group and the bromine. So then the important thing is, if you pick the other inversion, what they're looking for is, they being the chemist, that the OH and the Br are on opposites. One's coming at you, that is going away. Okay. Ozone, you cleave that, right? So we got 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. That becomes an aldehyde, and that's a ketone. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's ozone. Here we have mercury acetate. So this makes and we got methanol. So your intermediate here is going to be that mercury acetate called the mercurium ion. Because that's positive, and this is going to be electronically driven, where the methanol now is going to come in and open that. And then the mercury gets replaced with a hydride. So the molecule here, you don't have to show stereochemistry here. CH3 methyl, which you can, and then that gets the hydride. So you see how you have a Markovnikov, where you made an ether, a methyl ether. All right, but what if you do mercury acetate, and now water is what comes in here, and then that gives you the alcohol on that stereocenter, or not stereocenter, but carbon. This is regiochemistry. Hydrogen and palladium. You just want to show that the hydrogen is stereoselective, and it does come and add on the same side. Bromine here, you make your bromonium, and then the bromine will come, and since that's a positive three-membered ring, it's going to come more selective. And the important thing is, however you do it, that you have the bromines One's coming above the ring and the other one's going away from the ring. So these were the examples I think are probably the most important electrophilic addition reactions. I found these reactions on page 451 and 452 of your book. And then the last thing we're going to look at is the electrophilic additions for alkynes. All right, so let's look at reactions with a terminal alkyne. So we've done acid-base chemistry, so you should know that that's your base and this is your acid. You should be able to do this reaction, right? And then you make NH3, which is ammonia, pKa 35. What's the pKa of this? 25. Okay, so it's definitely going to make this molecule here in sodium amide, which is a strong base. And then you can add that onto, let's say, a ketone, right? And we've done stuff like that where that can get tetrahedral intermediate. And then you protonate to make the alcohol. That should be linear. I'm running out of room. Okay. What if you treat this with ozone and DMS? Because the triple bond, you're going to get a carboxylic acid, and then this carbon will be a carboxylic acid, but you'll still have the hydrogen there. So you're going to get two carboxylic acids, whereas when you do this with ozone, DMS, with the alkene, you get aldehydes. Okay, now the other thing that I think is important is to look at two reactions. The terminal alkyne, if you use diisolamyl boron, and then you treat that with sodium hydroxide and hydrogen peroxide, you're going to get the enol, kind of like what the donkey says, right? So you're going to get the OH on the last carbon, and then it's going to do an enol tautomerization. All right, so if you do the enol tautomerization, you get an aldehyde. Okay, but now if you treat this with mercury sulfate and sulfuric acid, you're going to get the addition on the internal carbon. So you get the internal carbon. And then when you do your enol tautomerization, you get a ketone instead of an aldehyde. Okay, so alkynes can go to ketones or aldehydes here. And then the other one you want to look at is the reduction. So let's look at an internal alkyne. Okay, so let's do three reactions. If you use, a lot of people put Lindlar's catalyst. You know, this is kind of like cooking. If you ask for the ingredients for everything that goes into a cake and you forget the eggs, it's not going to turn out right. Well, Lindlar's catalyst is just barium sulfate and quinoline on the palladium. Okay, that's what that is. But you need hydrogen gas. So, but I gave it to people. But if you don't have hydrogen with Lindlar's, then it's not right. Okay, and then the other third one is sodium metal and liquid ammonia. Okay, which I told you a long time ago that is not sodium amide. These are different. Okay, so what happens here, the first one, you're just going to get hydrogen added, and that's going to make butane. The next one, you're going to get cis. All right, so what's the name of that compound? That's 2, so you can write Z, 2-butene. Okay, here you're going to get trans. So that's 2-E-2-butene. So those are the differences. I think those reactions are worth mentioning. They're very important. And then if I look at your organic concepts, you can go over those, and you should be all right for organic too. And you have all those POGLs and stuff we've been doing all year. So good luck, and make sure you get onto Canvas and do the feedback quiz, because that's worth 5 points onto your final exam. See you on Monday.